All right, but I can still say good evening, ladies and gentlemen. Permit me to say that I want to welcome you to this evening's program. It's being organized by the Civil Technical Division, a subgroup called the Geo Group under the Civil Technical Division. Okay, the Civil Technical Division has probably now 6 subgroups now, right? About 6, and the Geo Group is one of them. So the Geo Group deals with geotechnical, physical, and other geo issues. And this evening, the Geo Group has decided to make a presentation, okay, about the practices happening in Ghana, and we want to discuss it. What we are doing here is to ensure that at least we all try to follow the best practices and see how we can update our knowledge. At the same time, what have we been doing wrong? What have we been doing correct or right? Is it correct to do what we are doing, or is it wrong to do what we are doing? I mean, we are all professionals. We want to have a kind of a harmonized system so that we all agree that this is the path we want to follow. That is all that professionalism is about. So we have decided to have 2 presentations today. What we're going to do is that we will allow our presenters to give out a presentation. Please note down all the necessary comments. When they are done, we open the floor for questions, comments, whatever. We want to put a consensus. My name is Engineer Joseph Odey. I'm the past chairman for the Civil Technical Division. Okay, so our first presentation is going to be on the case of inappropriate use of DCP tests equipment for geotechnical investigations for design of foundations of large structures. I'm sure you have the key items. Large items. Let's welcome one of our past presidents, Engineer Moniyan. Chief, you are welcome. All right, so to do this, we have our current chairman of the Civil Technical Division, Engineer Mike Obin Kunedu, to do that for us. So, Mike, you're welcome. Thank you very much. You can take away. You'll be here, and then you can use the pointer mouse to navigate into your slides. So this one is on.
Okay, good evening, or thank you, Chairman Yu. Like he said, I am a geotechnical practitioner. Unfortunately for me, I'm not the oldest practitioner in the room now. Until a few minutes ago, I was going to boast, but my head of department has come. And so, Chief, you are welcome. They are the people who held our hands when we started this in the early 90s. So we've been around for time. And we are able to see the growth of the industry. When we were at AESC then, I think there were 2 rigs, 2 percussion rigs, and then when we were there, 2 functioning percussion rigs, the others were blocks. And then we had an old rotary rig, later upgraded a bit. I remember that time we had a couple, BRI had a couple, and then Contera. Those are the ones I readily remember. So we are hoping that over the years, the numbers grew, and then the practice of technical investigations especially would really be standard. Unfortunately, that's not what we're seeing. I remember in 2016, Engineer Odey wrote a paper on availability of rigs for technical testing. That time when we counted, we were less than 10 in the country. But now I know that we have about 20. Going small. But there are certain practices which are hindering people's investment in these equipment. And those are some of the things that we want to talk about. Particularly when I see the DCP, I tend to be quite specific. When I say DCP, I mean DCP 8 kilogram, 0.575 mm drop. That for me is a DCP. So with that clarification, I will proceed. Now, the objective of the technical site investigation, basically, we're trying to assess the suitability of the site. In terms of the soil profile, material properties, ground strength, settlement potential, all these things. We're trying to obtain design for foundation designs. We're also supposed to be able to anticipate potential construction challenges and to estimate seismic response characteristics. These days of high-rise structures is very critical now. For me, for geotechnical site investigation, some conditions must be met. One, the reference standards for both field investigations and laboratory testing must be clearly stated as part of methodology. We don't do things arbitrarily. You must state what is your guide. The investigation must cover the full depth of foundation influence zone. When you put a structure on the surface of the earth, the load put on the ground affects a certain depth of ground. And we are interested in that full depth. We are not just interested in the 0.5 that where they're sitting, because we know that the load actually affects a certain depth of ground there. And we expect the investigation to go through that full depth, so that if there happens to be something weaker at the bottom, we will have an idea and know what to do. Third, the equipment that must deliver sufficient energy to the full depth of the influence zone. The results, of course, must be representative of the whole area of interest. And this fifth one, very critical. The field measurements that we take must be made to must be corrected to account for the energy losses. The hammers that we, depending on how the machine is built, if we say you are dropping 50 kilos, it doesn't mean that you get the energy from 50 kilos. There are all sorts of that affect it. And these things must be corrected for you to get an accurate idea about what the pressures are. So there's a hammer efficiency that has to be looked at. And as rods go longer and longer or go deeper into the ground, there is a certain effect on the results, overburden pressure and things. But the most important factor as far as the energy is concerned is the hammer efficiency. Let's bear that. Yeah. Oh. The depth of investigation, I mentioned it earlier, is critical for settlement analysis. It is influenced by the magnitude of the applied load. The bigger the load, the greater the depth that you must be interested in. And the depth of influence of the imposed load below the depth at which the load is applied. It's not necessarily just from the ground surface, but the effect takes place from beneath the loading point. And then, of course, geometry of the plan area of the stress area, if it's rectangular, if it is a strip, if it's a square, all those things affect the depth of investigation. There's some guidance for the depth of investigation. These days, the Eurocode has become very popular. Eurocode 7 is very clear. You know, when we started, I said that the reference standards must be clear. If you go to Eurocode 7, it tells us what the depth of influence should normally be. So you see the first one is a rectangular footing. So for a breadth, BF, it has a certain depth of influence. The other one is more like for a basement or a structure. That one also has a certain depth. The next slide gives us guidance on the depth. I jumped this one. So for high-rise structures and civil engineering, this is from Appendix B in the standard. It's not what I think. It is what standard says. This is for high-rise structures, civil engineering projects, the larger value of the following conditions should be applied. The ZA typically to be greater than or equal to 6 meters. But by this, it simply means that the minimum it must go is 6 meters. And the ZA is 3B. So for ZA, this is the first diagram on the left. So if it's a part footing, isolated part footing, what they are saying is that depth of influence, or you must go to a point 6 meters below the footing. If it is more like a basement structure, there's a BP, that one 3 times the width. That is what the standard says. And then there's also some guidance with the raft footing. So all I'm saying is that if you choose to operate under this standard, guide it by steps. Don't just do anything and then walk away. And then see that you are operating under the Euro code. Once you are guided by you're operating under this code, this is the guidance. Okay. Typically, how do we do this geotechnical investigation? We have the geotechnical side for drilling, SPT sampling, pit excavation, plate load test, dynamic moving with window sampling, cone penetration, all that the geotechnical one, intrusive methodologies. Then we also have the physical, which to a large extent either seismic or at times use electrical resistivity. So the combination of these two approaches tend to give a very comprehensive and representative data. If you combine them well, the information you get, you can do a good design. When you hear that there's a tremor, you don't wake up at night thinking, is that my project or what? That's the whole thing about doing the right and using the standards. So if you combine two for a typical field investigation, you can sleep well. So let's look at the approaches. The standard penetration test. Under the Eurocode, that's the reference, BSD and ISO. Now all countries have combined their standards together and have a unified group. And under this unified 2247 part, they have a standard penetration test. Everything you need to know is there. So this is the most universally accepted geotech field test procedure for assessing ground strength for structural foundations. Very useful in granular material, especially when you have sand and gravels, which tend to be difficult. So that for me is a standard practice. So all the other things we do, we are trying to work towards that. It has a very high hammer driving energy, 238 kilojoules per meter squared. And because of this level of energy, it is able to penetrate most types of soil formations, at least the ones that we encounter in this country. So the full influence zone is covered, typically up to 15 meters, at times 120 meters well before. So when you use the SPT, that is actually the standard, but it is not always that good access to the SPT, but that is the standard practice. It has ancillary tools that allow you to go through very hard material, chisels and all those things, so that the whole idea about SPT rig is that it covers the depth influence zone. It does not go and hit a small obstacle and say, okay, it's all right, and then we'll write the report. No. And it sets the standard for all the other test equipment. A lot of geotechnical correlations is based on the SPT N60. The N60 just means that the field results have what's the term? They've accounted for all the energy losses and all those things. They've corrected the values for hammer efficiency, length of rod, size of borehole, whatever. So the SPT N60 is the standard. That's the reference. So in this kind of way, we talk about fusel. the concept of refusal is based actually on the SPT hammer energy not being able to penetrate. That is when you have refusal. Not when you have just a small wave bouncing and say you have refusal in the ground. No. You must have something of the level of 238 kilojoules per meter squared. If it is not penetrate soil, then we know that yes, we have refusal. So the SPT is a standard. But in addition to the SPT, there are other approaches. Dynamic probing for foundation investigation. That is the same standard, the part 2. So BSEN ISO 22476 part 2 talks about dynamic probing, part 3 standard penetration test. Now, the dynamic probing describes 4 procedures and is differentiated primarily by the hammer weights. There's a DPL, which stands for dynamic probing light. We have dynamic probing medium, dynamic probing heavy, and dynamic probing super heavy. They all have the energy levels. Now, the basis for selecting which type to use should be the drive energy. And the driving energy, basically, the hammer must drop by gravity, free fall for a certain distance. For the SPT, it is 63.5, dropping 750, 760 millimeters. That is the hammer energy. These 4 all have energies. So in any particular situation, you must look at your formation. And that's how come we say this geotech business should be done by people who understand the geotech thing and the geology and all that. You must look at the formation before you decide what one to go for. Bear in mind that you have to go through full depth of influence. Please. Okay, so results from these things, the DPL. The DPL actually is just a proving, it's the dropping weight driving the rod into the ground. It does not by itself collect samples. But the equipment can be configured to give you samples. But the DPL test itself, the dynamic probing test itself, does not direct you samples. But make sure you pick samples. So results can be used in combination with in situ samplers. There's a sampler called the Waco sampler. You can also fix a standard SPT sampler, split spool. You can fix it to a dynamic probing rig if you know how. And when you've been around long enough, you know how it's not anything strange. When you do that, when you have the sample and then you have the test results, then your profile, you can describe the profile better. So the results may be used for the determination of strength and formation properties of the soil through appropriate correlations. And in doing this, you must bear in mind that geotechnical and equipment factors can influence both the operation of the equipment and the results of the test. If your hammer energy is not strong enough, just one pebble, one in the ground, will disorganize you. That is a technical factor. If your rod is not strong, it can bend. That is an equipment factor. So all these things you must bear in mind as you are carrying out the investigation. And all these things affect the results of the test. All of them. Simple pebble. And people say that they get refusal. And reports are written based on that. Okay, so let's have a look at the 4 types of dynamic probing apparatus. The reference is still the 22476 part. All of this is just extracted from it. None of it is mine. This is in the standard. Okay, so the hammer mass. The DPL, which is the light equipment, it has a hammer mass of around 10 kg, plus or minus 0.1. There's an intermediate one which has 30. And then you come dynamic probing heavy. That one is a 50 kilogram drop weight. And then the DPSH, I have to be there because they are basically different types of DPSH. Some of them they prefer to use the 20 centimeter increment to measure and things, but the DPSHB typically is 10 centimeter depth intervals. So the height of 4, the DPL drops 500 millimeters, DPM 500, DPH 500, and the DPS drops 750. So the DPSH, in terms of energy, actually is equivalent to the standard penetration test rate. So the rods who play a part in the interpretation of the ISO, you must know the weights vary. The 6, the lightest one is 6, goes to 18, 18, and the DPSH guide rod mass up is 30 kilograms. The cone angles also, all of these are 90-degree cones. But I must say that the DPSH, some of them have 60-degree cones. So you must know the cone angle you're working with because the results are affected by the cone angles. The cone has a base area, 10, 15, 16, 20. The base diameters are there. The guide rod masses, all of this is there. The last one, the one that's really interesting, the lightweight DP has a top specific work per blow of 50 kilogram per meter squared. So, boom, and then the cone area 50. It goes to 100, 167. And you see that the DPSH is 238. When you go back to the SPT, it has the same value, 238. The difference between the SPT and the DPSH is the fact that the SPT drives an open sampler, and the SPT is carried out in a borehole. So because of that, there are a lot of energy losses in the DPSH which don't occur in the SPT. So all those you must go before you try to interpret the results. Don't just equate. I've seen reports, some people think that the two are the same. They are not. They are not. The side friction is different. All sorts of things are different, but you must have this basis before you can have a good appreciation of what's happening. So this is the information on the 4 types. And like I prepared, these are dynamic probing. So normally when I say DCP, I don't need any of this. I do not mean the light system. That is for me is not DCP. So my sermon here today is not on the DPL. I am talking of the DCP evaluation of dynamic probing results. Okay. You see, when you use this to generate full results, they must be evaluated quantitatively before you can do anything with it. Now, the principle is that though we say the thing has an energy of 238, that is a theoretical maximum. Each machine has its own peculiarities. So in reality, we do not get 238. So, roughly speaking, we have to calibrate these rigs for each one to the same thing we do with concrete cube classic machines. The same thing we do with the Schmidt hammer. And every machine must have its own factor, so that when you are doing work, you are a bit confident. So once you calibrate it properly, you get to know what the actual energy is. And in certain countries, they are very, very insistent on that. So South Africa and things, you can't just go and put any machine there, say this one, this weight. No, it doesn't work that way. And the consideration should be given to the influence of rod friction by side addition and rod bending on the recorded test values. Those of us who've done DCPI a lot, when you finish, we have to bring it out of the soil, you know that something is holding it. You know, so don't just hit and say this and walk away. You have to take all of this into consideration as you're processing the data. And at the end of the day, you have something called a dynamic point resistance. And when you determine this one problem, then you can move ahead to the stage of soil bearing pressure. I will not say soil bearing capacity at this point. I will say, but the soil bearing pressure. So the ultimate is actually to determine the dynamic point resistance, and then we use that with the quantitative assessment. Then we come to this. Basically, what is it? It has a drop weight of 8 kilograms. The annual and guide rod weight is normally around 6 kg. It has a drop height of 575. It's 575 millimeters. That is the drop height of the DCP. And as such, the maximum energy it can deliver is 46 joules. That is mass acceleration due to gravity drop height using 46. But this 46 actually is not the other entity I was referring to. This is not the work per area. When you do the work per area, you come to 92 kilojoules per meter squared. But this is just the energy, that the kinetic energy that becomes what potential energy. The diameter of it is typically around 20 mm. It has a cone angle of 60 degrees. The effective investigation depth is 800 mm. This one is literature, basic literature, but it can be extended to 1,500. But the effective depth of a standalone DCP is 800 mm. Primarily is used for in-situ strength of flexible pavement made of unbound material, found road embankments and things like that. That is the primary use of it. When you use it properly here, you don't have a problem with anybody. So let's compare the DCP and DPL. The hammer mass, the DCP is 8, the DPL is 10. The drop height, one is 575, one is 500. The cone areas, one is 5, one is 10. Cone diameter, see the difference between the two. One is 20 and one is 35.2. And then the rod diameter. So the first point of interest, you see the cone diameter and the rod diameter. When you take one from the other, you get the angles around the rod. 4M for DCP. So those of us who grade, when you have 4M split by 2, you are talking of 2 mm on each side of the rod. Sand. So once it enters the ground, it's moving with sand. I mean, the friction is so high that you can't believe it. But look at the DPL. It's 35.7 and 22. The allowance is bigger. It is designed to try and minimize the side friction. So there is a difference between the two. A lot of time, the last one see there, a lot of time, just write the energy. If you just write the energy of the two, one is 46, one is 50. You think that they are close. But then the energy is applied to a certain area. When you do that, one is 92, one is 50. There's a difference. So the cone areas, the DPL times that of the DCP. And the DCP side friction is far, far, far bigger than the DPL. The limitations of the DCP. When you go into the standard I referred to, Annex D gives you some ideas about what the limitations of the, actually is the DPL, which now we can compare to this thing. The driving energy really is not much, so it's not able to penetrate dense soil strata, especially when there are pockets of sandy gravel, composed rocks at shallow depth. It really can. Then, like I mentioned earlier, there are significant energy losses to side friction due to the extremely small clearance around the drive rods. So actually, after one that when you start getting large flow counts, they are not necessarily because the foundation, the formation is dense. No. It's because you have a whole lot of friction and you are moving with it. So you are working at friction. It's not the end bearing that is the issue now. It's the friction along the side rods. And this can do a lot of interpretations. And it has led to them. So the cumulative energy losses from inertia. Look, as you add rods, the metal tends to absorb a lot of the impact energy. And then the side friction also increases. So you see that the effective depth of testing of the influence zone is not much. So I just give an example here. If you have a path, let's say 1 meter width, and you place it at a depth of 1 meter, by the guidance given us up there, it means you must investigate at least 4 meters. If you have not investigated 4 meters, you cannot tell us a 1.2 meter footing at 1 meter. That is all it says. But you see reports where we have 0.5, 0.8, 1, and they are saying that we should put the footing at 1.2, 1.5. When the thing hasn't reached there, how much more the depth of influence? And some of these buildings are 6 stories. So another thing about the meter penetration depth is that when there's a slight weaker zone, you won't see it. You only see the stubborn layer that you are struggling in. And people tend to assume that, oh, if it's hard at 0.5 or 0.8, it means we are approaching the rock. It's a very, very dangerous assumption. The overall effect is that the DCP test is not able to accurately generate information about the ground strength conditions of soil from below that depth. Normally, if you find a DCP going to 3 meters and things, then it means the soil is soft or it's loose material or whatever. These are some of the observations we made from the DCP reports. You see 2 to 3 points and 1 test pit used for investigation for buildings from 3 stories to 6 stories. It's a very common observation here. Very, very common. 0.5 meters, 0.8, at times close to 2 meters. Okay, fine, 2 meters. Then you see 2. And the interesting thing is that DCP can reach 2 meters, but the pit cannot go beyond 1 meter or 1.2. So they don't know what is there. And they say we should put foundations down there. It is a very, very worrisome observation that we have made. So typical in they are made between 0.5 and 1.5. If you take 100 DCP reports, about 80 to 80, whatever would be around that depth. That's where they terminate them. Then you add 1 pit to it, and then make a declaration for the whole site. So within a day, they are finished. And on. So, and when they do, yes, 1.2. All right. Then they stop. And then add a 2A. And then you will find very, very high carrying capacities assigned depths of 0.5 to 1.2. Especially in the gravelly, sandy, these are lateritic soils. Oh, right. We have it all the time. And in the reports, you will find that people put photographs of DCP. Clearly, it's a DCP that is operating. But then the dimensions they are using are for DPL. It's a very common observation. Some of them, the photograph actually has, let's say, you see 8 kilos, the weights are there. Meanwhile, the calculations, they are using the dimensions of the light dynamic probe. And the last, the bearing capacity, they are based on these two formulas. One says that the Q ultimate is equal to 30R. R is number of volts, by the way. And another school of thought says that the Q, the 30R is the Q allowable. The same 30R. Some of the reports is ultimate, some is allowable. I don't know where the thing comes from, the equation. So I've searched, so I cannot query it too much. But this is what we see in the reports. It's very, very common. Some say it's all, some say it's allowed. Those who say it is ultimate will then come and divide by 3 to get the allowed. Those who say it's allowed will take it straight up. And you have huge bearing capacity. Okay. So how much time? I will be checking. Okay. Okay. So the first issue I have is the bearing capacity formula. Q allowable is equal to 30R. It took me a long time to find where it is coming from. But eventually the door was shown to me. I'm sure through prayer and meditation and things, but I was shown the light. It is based on the Dutch formula as expressed like M squared H over AEMP. M is the drop weight, H drop height, A the area of cone, E is the penetration rate. And you see, the area of the cone is very, very important. That's how come I pointed it out.
Like a roll.
No. In this one, the rows and things are all captured in the P. The small m is the same as the big M. It's a hammer weight. The P is the anvil and the rods. The M is the hammer, so the same M there. But you see, interesting enough, people tend to forget that this thing, it has units. The units for the art, when the Dutch formula is written this way, is decantation per centimeter squared. How many of you have ever heard of decant? Even my head of department, who brought the reference book from Holland, he brought the reference, Sanglare, original. He was the first person to bring into the country. It's decant per meter squared, or simply expressed as bar. The pressure is bar. For some reason, people think that the unit of this is kPa. It is a very serious error. Extremely serious error for professional engineers to make. The unit is decant per meter squared, simply put bar. So the M is kg, the P is also kg, but the P, like I said, is the anvil plus the rod weight. The H is centimeters for this formula as written. The A is centimeter squared, and then the E is the blows for that thing. So this is how to write it. When you put it like this, then they will say M squared H over AE is equal to 6250 over E. The E is 10 divided by the number of blows. It will bring you to 625R. This thing is valid only if you write, you see the A. If you put the A 0.00 M in meters and the H in meters, that is the only way you get this. If you put it as up there, you end up with a situation where you have, I think it's 62.5. People are trying this. Some strange thing, unless I am not getting it right, but somebody proved me wrong. This one, I'm ready for correction. So this 625R, which when they come down, they divide it by 20 to get 31, where we round it off 30R, and then they give it the units of kPa. Sanglare. Sanglare has done a lot of thinking and writing. So we who are disciples, our sector of 20 is something to do with pile driving and things. If you divide it by 20, it gives you a factor of safety of 4, the equivalent of a factor of safety of 4. So that's how it drives. You see, but like I'm saying, if you use the unit properly, you will not get a 65. And so this whole business of 30R is 30R with the KPA is a bit of a challenge. So that's the first issue. I am waiting for another government representation and explain this thing to us. But all over when you get a report, see, it can be shown that Q is equal to 30R, then they multiply. That is what is in all the reports. It can be shown that there was only one guy who was gracious enough to bring the 6250. Then I began to see the light. I said, this is where it's coming from. So this is issue number one. This formula, I'm not saying it's wrong. All I'm saying at this point in time, I don't understand it. If I go strictly by first principles, using the units and things, it doesn't work for me. I cannot say it is wrong because it's used by so many people that somehow they must know something the rest of us don't. We just threw out the challenge, bring somebody here. He will also come and do the revision for us. Once we understand, we'll move ahead and see how. Issue number two, the cumulative effect of the rod. Once you decide to go by this and you accept 30R, then you must account every rod that you put in the string. So the first one actually is just for 1 meter. For 1 meter, when you have one rod, that's when you have these and things. Immediately it goes to 2 rods, the weights change. So for the first one, when it's 1 rod, the rod is about 3 kilograms or so. The M plus P is 16. Then the RD will give you this 625. Then you have your 30R. Then do your magic. When you go beyond the length of 1, meaning you are in the 2 meter zone, the rod weights change. So corresponding to this thing will change, and it drops from 30 to 26. For those who are able to go to 3 meters, the factor will change. Unfortunately, what we see is that it's a flat 30R. And that is where the danger is. Because when the thing is dropping and you are forcing it, it could be very, very dangerous. Sorry. So these are the factors. If you intend to use a 30R, then you must compensate for the weights of the additional rods. So taking this allowable bearing capacity expression as it is, issues that contribute to the errors. Like I said, that simplified formula does not address the issue of the units well. It's not clear. It's something that has to be clarified. Then the other thing I said, all the DCP device that is used for the test, the calculations are typically based on the DPL dimensions. In fact, I forgot one. Let me show you something. This one, you see, the M is 10, right? So that 10 is a DPL weight. The drop height 0.5. That is the DPL. But then the area that is used in the calculation is 5. If you use the correct DPL area there, it will have this, because it's double. Immediately you do that, move from 625 to 313. So if you are somebody who does times 30 and then you correct there, now you are times 15, it halves the thing that you are using. So this thing is very problematic. Whatever assumptions have been made must be looked at critically. For just that one factor, the area, are you using a DPL area or are you using a TCP area? One is times the other. And just by that, you have the so-called bearing capacity. Okay. So the other approach, you see, let me finish this. So the simplified doesn't address the US property. I'm saying that you're using a PC device, but using your dimension, and the two are not the same. You're not interchangeable. We are, yes, must appreciate that. The weight effects of the additional rods are not factored into the computations. And of course, the field measurements are not corrected for energy losses and friction losses. So the data we are working with right from the beginning is wrong. According to research, typical energy transfer ratios in these hammer systems, for especially the manual one, we range between 0.4 to 0.6. And the DCP release is manual. And if you watch the boy doing it, he does the first maybe 50, then you see that time it doesn't hit the top of 6. It's tight. It's tight. So you are not getting nowhere, and they are telling you that it's 0.4 to 0.6. So you think you are dropping a 10 kilo weight, but the effect is instead of 10 kilo times 0.5, now have 10 kilo. You now have same 10 kilo times maybe 0.3. G. The DPC. So the overall effect is a gross estimation of the soil, estimation of the soil resistance. Then the other approach. When we started, I said clearly that you must state the standard that you are working. When you use the standard, things like for you, this same standard is there. BSPNI 247 start 2005 and next. It gives guidance as to how to interpret this data. There's something called the unit resistance. That is the energy that is released over there. So it's actually the work done. That's the MPH over AE. The unit is in pascals. Then you do something called the dynamic resistance. The dynamic resistance accounts for the weights that you are using. The drop weight, the weight of the rods, whatever. So this is how the expression is. M over M plus MA plus MA. MA is the angle and the guide rod is in kilograms. MR is total mass rods which are put into the system at any time. It's in kilograms. The mass of the armor is in kilograms. Then, of course, John acceleration due to gravity. The height of fall for this expression is in meters. The cone area is in meters squared. And then the blows to penetration rate per meter. That's how it's expressed. When you do it that way, you get this form of the Dutch formula. The other one is the Dutch formula, but they are different when they write it that way. When you do the simple one like this, it's clear. M squared GH over AE. And you see the other difference between this one and that one. Here you see the G, acceleration due to gravity. It is featured. The other one is not featured. Why I don't know, but it's also in books, but you don't see this clearly. When you use this form of the Dutch formula, and then you apply your data collection, you find very, very interesting results. Here, people, of course, as I said, disciples of Sanglare, you divide by 50, the factor of C approximates 4. Actually, either 20 from 20 to 22, depends on the soil condition. For a time, it's 20 that's used. But you must know the soil conditions for which you will use a 22. So I did a very simple comparison for you. Data. This is from an existing site in a report. Depth, he was able to reach 1.7 meters. And these are the clues, the M10, 7, 15, and then at 50, he declared that his refusal. So the test was terminated. So then he plotted. When he plotted, that is the red line. So you see the is in KPA. When you use the raw Q is equal to 30R. This is the Q to 30R presentation. When you use it like that, you see that you get a red line. Like so, and then you see that at 1.8 meters, you found a bearing capacity of 1,500 kPa. When you use that formula, as I showed you on the previous slide, you will get a blue line. You see the difference between the two. So the common practice we have now gives the red line as the variation of bearing capacity with depth on that side. When you use a formula, that formula I showed you, all ones, and it's because it is compensating for the weight of the rods as you go. So this one terminates at around 5, maybe, I don't know, 5 or 600. And this one is 3 times that because it's 30R. This is what I want to draw your mind. We have this red situation all over now. But with a little bit of care, it will not swallow. And even this blue line is because we haven't actually taken care of the energy losses in any way. I just took the raw data and then put it like this. So if you were to really take out the losses due to friction and the hammer efficiency and things, the thing would move closer. So there's a huge overestimation of the bearing capacity of the soil when you go in Q is equal to 30R. So even accepting that as a valid expression, this is the danger that is to us. And we can do this because in this country, you do it and it seems you can walk away. Nobody can hold you. But when a professional like starts kicking it, then we'll see. Implications of the erroneous results. For the red one, it's all an error. There's overestimation of bearing strength of the resistance on layers. There's a masking of the presence of weak zones. We need more because at one point, it stopped at 1.7. For this particular one, the bearing footing depth is 1.4. He stopped at 1.7. He recommends a footing depth of 1.4. And then 1.4, you know that it will, by all means, extend to our 4 meters, the influence, but we don't know what is there. Termination of investigation without penetrating the depth of foundation influence. Instead of doing about 4, he did 1.7. The machine was tired, quit. And then it gives a very erroneous basis for applying geotechnical correlations. All those correlations are based on something similar to the SPTL value. Now, I decided to show some examples. You see, the DPSH machine is very much like the SPT. It's been used all over the country. Now, what you see here, if this was Banta graph, you see that around 1 is huge. But because that machine can persist, it broke through it and then it just dropped. So if they had stopped at 1 meter and said that, oh, it's 900, so let's say use 500, that's safe. Everything below 1.5, look away. And there are I have a lot of examples of this. This one is the Kumasi, so embankment. Within the first 1 meter, see where the things are with the pressure, 800, 1,000. This is with a DPSH machine. But after 1 meter, it just punched through the layer. And for some of them, when you the rod drops, it hits the handle. This is Kumasi. This is Tema. Tema towards the hub. We have this it's all over the place. The first 1 meter. Then you see where the things are. It's after 4 meters that start hitting something. So if you do 1 meter with your DCP and you think that you are hook free, you're joking. Because when you excavate and put it at 1 meter, the load comes, it will just fall. So we done have Banda. The second one was the Kumasi. This is Tema. This is North Road. Similar. Conclusions. Results of the lightweight DCP. 8-kilogram apparatus. The results are typically exact at depth because of the high energy losses that diminish the impact energy of the armor system. So typically, results from flow through tests are significantly affected and therefore not representative of the true state of affairs. That is conclusion one. Now, this one I've seen red. What we've seen is that because this DCP thing has become so rampant, it is undermining our efforts to attract investments in standard geotechnical equipment. Between the time Engineer Ode wrote that and now, I'm saying that it almost tripled what was in the country. Now it's flat out because the machines are mostly standing idle. People are walking around with DCP, and then with that kind of queue is equal to 30 hours. That's all. So the machines are standing. So it is not an issue that we don't have it in this country. The issue is that we are not rotating well enough, and because of that, all that investment is standing idle, and people are doing the wrong. They are doing the wrong all over the place. So I'm concluding that the use of the DCP test equipment as the primary field test device should be discouraged. That is my conclusion. But I'm not just ending there. What's the way forward? I am saying that the GHI should collaborate with the Engineering Council and the Ghana Standards Authority to ensure the following. One, to prohibit the use of the DCP test equipment for geotechnical site testing for buildings that require building approval. You don't require a permit, you want data rates, fine. You want to do parking lot, fine. Small embankment, fine. Pipeline, route assessment, fine. But not for 4-story, 5-story. We've even seen one for 6 stories. It's all over the place. As if we and moving forward, I am campaigning that every ground investigation test rig should be registered. The same way Ministry of Works or whatever registers, all this kind of thing. Every equipment like that should be registered, and then we should calibrate them. The calibration is not difficult. We should calibrate them so that we have the energy efficiency factor specific to each rig. So that when you generate results, we can interpret them and use them safely. And also that we should register and certify all laboratories that are offering engineering soil testing and construction quality control in support of these investigations. We have people just can't do anything, and then because it affects people's investments. Please. 4, the GHI should develop standard guidelines for timely review of geotech investigation reports that also ensure traceability of the field equipment. This traceability is linked to the calibration and registration of the rig. I put the timely into bold because look, all the reports that I reviewed before writing this 4 years ago, 6 years ago. I mean, it takes such a long time before it comes for the permit thing that I don't know. But somehow it has to come up early so that if it has to be addressed properly, then we do something. And I am also saying that engineers who sign these things must have professional indemnity cover. Yes. All of you should sign, you must. Be back. To be engineer. And then the last one, which is also a very interesting thing, is because what there's a cabal. It's like a black market. You technical report. It's a whole black market. People sit in this location and then do it for this one. It shouldn't happen. Once you are a staff of approving authority, you should not write these reports. And you can't say that I am in this assembly and no. All the years the assembly time have one employer, the local government. You can move it from here to there to there. That's what happens. So once you are an employee, you shouldn't be participating. Yours is to review board this up. And it is happening now. It's a serious conflict of interest situation. Let me just share a photo of, just to give us an idea of what we are doing. The one you see on the left is a dynamic probing rig, super heavy. It's the same principle as the one on the right. The one on the left has 238 kilojoules per meter squared impact. Boom. The one on the right, the DT, that one has a 92. The difference is so big. So if you try to replicate the work of this by simply adding 30 to everything, you are putting those investments at risk. Is that the scale of the difference that we are talking about? This actually is equivalent to an STP machine. Yes, that this one has suffered with the friction losses and all that. And that's the so it's this kind of thing that we are talking about. I'm done. Thank you.
Oh, okay. Thank you very much. Nyache, I don't see your yana. You see, because this subject of or aspect of geotech is highly controversial, we are having 100 people online. Seriously speaking, when it comes to the question, I also add my words the conflicts or the kind of errors we have with DCP. But I won't talk too much. We want to move on to the second presentation. And you know what? Are you ready? No, we want to move fast so that you put your question. We want the second presentation to come. Otherwise, I tell you, please don't go. Then. No, don't go. In the Africa, you can't go. No. Solo is here. So, Kofi Enyinabwatin will be talking about another aspect of site investigation. By this time, what Engineer Pedro did is more of an invasive approach, the DCP, blah, blah, blah. But Engineer Bwatin talk about the non-invasive, which is more of physics, how we also incorporate to physics in our site investigation. And it has become another useful area that helps technical practice. We cannot cheat away. So we allow people to start the process for us.
Good evening. Thank you all for being here this evening. I know time is already fast, so I wouldn't waste our time. I'll go straight to the topic that I have for you today. What I'm going to present to you is seismic MASW as part of being used for geotechnical site investigations, and also the horizontal to vertical spectral ratio, which is passive seismic. The outline for the presentation is as follows. What is MASW? How we provide data? The result of MASW? What information does it provide? That will help us in whatever design considerations that we make. And then the application and advantages of MASW, the passive seismic horizontal to vertical spectral ratio, as many people call it, HVSR. And then I conclude. MASW is an acronym for Multichannel Analysis of Surface Waves. It was first developed by Chu Park, Miller, and Zia in 1999, when Chu Park and et al. Were all with Kansas Geological Survey back 1999. But Chu Park has moved on to set up Park Seismic, LLC, and is no more with Kansas Geological Survey. A typical MASW requires a seismic source, which usually is a hammer. We normally use the 8 kg, 9 kg, a weight drop of 50 kg, depending on which of them is available to use. And a two set of geophones or more. That is why it's called a multi-channel analysis. The seismic source that can be used for MASW could be active or the passive. When we say the active, that is where we use the seismic hammer, any weight drop, automatic weight drop. When we talk of the passive, we're talking about conducting the survey in a very busy area, especially in cities, close to railway lines or heavy traffic areas. The propagation velocities of the surface wave through the subsurface material are then analyzed. When we inject the energy source into the ground, we have a waveform which is generated through the medium or subsurface material, which then produces a dispersion image. And out of that dispersion image, we're able to see the subsurface material characteristics with respect to the energy that goes through. And through that, we do what we call the picking of the fundamental mode, areas of high energy within the subsurface. And then we get a depth profile for the velocity. This is how we acquire seismic MASW data in the field. The first picture you see there was recently conducted in Ivory Coast at a newly constructed mine, I think the Lafayette project site in Dabakala. Over there, we had a series of line conduct. So we use the line streamer. That works faster compared with using the one we have in the second picture, which is around the TUC area in Accra, where we have a normal planted with a spike planted into the ground and all that. And then again, another area, secondly, somewhere in Western region, we again use the line streamer. So you hammer onto a nylon strike plate, the energy goes into the ground and it disperses. The dispersion is then analyzed and then come out with the phase velocities in each of the dispersion images. And from there, we're able to get the depth profile, the VS depth profile for the subsurface. This is the same site in Côte d'Ivoire around the primary and secondary crusher area. The designers of the plant or the crusher area wanted certain parameters to be used for their design. And that was basically the J, the shear modulus, and the elastic moduli of the subsurface material. Again, another site within the same area, the screening area on the same Lafayette Gold project site. Like I said earlier, once we inject the energy into the ground, we generate a wave. And these harmonics or waves are amplified the number of geophones that you might connect or you might have during your survey. In this case, we had a 24-channel geophone. So you can see about 24 of these harmonics forming a wave, which propagated through the ground. And that is the second image is the dispersion characteristics of the energy that we introduce into the ground. And that is the response that the ground also showed. So based on that, you see, unfortunately, you can't see the horizontal axis, which is the frequency. And I think from 50 hertz to about, let's say 25 hertz, we have a constant velocity throughout, which is an indication of a similar medium or a material of the same type. And then it changes from the 25 going up all the way to about 10 hertz, telling us that it has refracted or changed the medium or have a second medium, which is much stiffer because the velocity there tends to be increasing from the norm. So from the dispersion image, we're able to do the picking or the picking of the fundamental mode, those the high energy areas within the dispersion image, and then come out with a 1P profile, depth profile for the 1P velocity depth profile. for the site that's under investigation. For this site, for instance, you could see how the shear wave velocity differs all the way from 0 to within the top 30 meters. We're talking about, let's say, 250 meters per second for the top, about 0.5 per meter, and then it changes all the way within 0 to 10. It ranges between 250 to about 300, an indication of a stiff material. And beyond that, it changes. You can see it changes all the way from the surface up from 10 meters all the way down to about 12 meters. It changes again, and you see the velocity that we are measuring there, about 525, 50, thereabout. So if we're able to generate a series of these 1D profiles, this very one today, along the same stretch, we should be able to come up a section like this, which gives you a continuous profile along the whole surface area. If you have, let's say, a 1 kilometer line, 500 meters, 700 meters, we can continuously gather and provide you with a section, a 2D section, for you to understand the ground, how it's behaving. And for this particular site, I think it's the same secondary crusher area, the BLCL, just the center line of it, the axis of the crusher area. That is how they named it. And we could see where they terminated, you could see where they terminated this borehole BHPS01. They terminated around 7-8 meters thereabout. And for borehole BHPS02, that went all the way to about 27 meters. We had information on borehole PS02. And we tried to correlate and get a better understanding if the geophysics was really correct in supporting whatever the borings information that was provided, or it wasn't good enough. And by doing so, we were able to infer and indicate to the client that this particular area where they wanted to put up the secondary crusher, you have the bedrock being much shallower compared with where they had the primary crusher position. And if you look at borehole logs, you can see within the top 0 to 3 meters, or let me put it 5 meters, thereabout, up to somewhere there, you can compare the velocities. And then the velocity changes around 8 meters thereabout to be around 400, 450 meters per second and reduces again. The reduction in shear wave is an indication that we are having some fracturing within the soft surface. Shear wave velocity don't go through water. Shear wave velocity does. So whenever you have low shear wave velocities at deeper depth, it's an indication of either fracturing or an intrusion of a less deeper material. So we compare these logs with our 2D section and correlate. It made a lot of sense. But one thing with MASW is that you need to have a clear understanding of where your fundamental modes are. Because the moment you get your picks wrong, everything about your VS profile will be wrong. So we continued again, and then compared, and this borehole terminated, I think, around about 28 meters, which made a lot of sense with what we did for the client. So they were free and very confident to use the G and then the last modular parameters that into the Poisson ratio and all that. Now, so what information does MASW provide? Shear wave velocity is a direct indicator of ground stiffness. We talk about stiffness, we're talking about the resistant formation, which is ultimately related to what? The ground plastic moduli. So VS is also one of the elastic constant and closely related to the shear modulus, Young modulus, and commonly used to derive other engineering dynamic parameters. So out of the VS, we're able to calculate or derive the Young's modulus, the elastic moduli. We're able to also get the shear modulus. We're able to get or calculate the Poisson ratio. We're able to also deduce the density for the subsurface material because the shear modulus, the VS, and density are related. We're able to also come out with some estimated SPTN values. I mean, I've done this with a couple of sites and they are not far off. And we're able to also come out with a site-specific peak ground acceleration value. Once we're able to measure an accurate VS, we should be able to come out a PGA site-specific. Knowing the VS, having the thicknesses of whichever layers that you have, and also the bulk density for the material within every layer. With the VS, we're able to provide information on the site class. These days, you get scope of works, clients are requesting you to give them the site-specific class for a particular site. If you have to go with only the geotechnical borings, I'm not sure we'll be in the position to be able to give them that information. But here we are, we have all the equipment that we can institute or we can measure the VS institute and provide the site-specific class. If it's class A under the Euro code, I normally use the Euro code A site for my report. As most of our peers here, the Geotech reports that some of our groups also prepare, most of them use the same Euro code 8. So I use the Euro code, but once you have the VS, you can choose to decide whether you want to use the UBC universal code or the NHEAP. You want to use, there are several, the Canadians, they have, the Australians, they have their code. I remember for that particular survey, I was using the Euro code 8, but Australian consultant said, no, he wanted to use their own code. So I just gave the VS and he will use it the way he wants. The VS can also be used to evaluate compaction and gravity. And one thing I also noticed during our survey, especially at Dabakala, where we saw them doing compaction at the site, was that, I will come back, I'll flip back. If you look at this site here, the primary and secondary crusher area, I noticed that the compaction level here, compared with that of the sedge bin area, this area, looks much better because the velocities within the top 5 meters were much higher compared with what we witnessed within the primary and secondary crusher area. VS again can be used to also detect the bedrock velocities. As I was saying in my previous slide with the dispersion image, where I indicated a detection point around, let's say about 20 hertz, where the velocities, the phase velocity begin to change. It's an indication that the medium is changing and we expect that to be a very stiffer material. We can also use the VS as an approximate method for subgrade reaction calculations. And I came across some pump tests by Gazettas, 1983, which Engineer Day also shared with me. And that's what he has been using. So for the bedrock mapping, this is a typical site around Bridge. We conducted a visual MASW, and there were some boreholes drilled. So we tried to again compare with our report. And this borehole 4, this is where it terminated. Borehole 1 went all the way to, I think, 15, 20 meters thereabout, because there was some pouring canals. So we were able to infer that beyond here, around 10 meters along the same line, this is how ground formation was behaving. You can see the bedrock is not constant throughout. If you have to connect these two boreholes, ideally, people might say, or some might say, because we terminated this year and this one is the bedrock straight along here. No, but you can see the rock head changes with the topo as well. So again, like I'm saying here, the shear wave velocity or MASW is able to give an indication as to how the rock profile or the bedrock profile itself is. Again, we can also use the VS once obtained to model and come out with the site-specific PGA. Usually, I choose to use the Chichi magnitude 7.7 earthquake. I think this happened in 1999 in Taiwan, thereabout. I know we haven't experienced magnitude 7.7 earthquake in Ghana yet, but that is what I normally use for my model. I go to the extreme to use to model and get a site-specific PGA with depth. So this is a typical example for this same site, on this particular line. We were able to come out with a site-specific PGA using the VS obtained for that line. So with the Chichi, we input the acceleration time history or the ground motion into the deep soil software, which I normally use for the PGA determination. And the model with the site-specific VS that we measure. So the PGA that we obtain is specific to the site. We don't use any hypothetical values. Okay, around Accra, this part, maybe let's use 0.3. This is in situ measure. And it cut cost. Probably about the site, I remember one of the sites around Anabraka, they proposed to use a site class of C. But after our investigations, the site itself was class B. And this is a huge cost difference. There is a huge cost difference. Having to design based on site class C and having to design based on site class B. So with MASW, this is the Eurocode 8 seismic site classification. I picked up from PackSize software, which is what I normally use for my MASW data analysis. For site class A, you can see the velocity, the VS should be greater than 800 meters per second. For class B, it's giving us a range between 360 to 800. And from there, you can also expect to have an SPT value greater than 50. Class C2 is here. It's talking about deposit of dense, medium dense, gravel, steep, clay, and all that. Also, the velocity range is between 1 and 360. And we expect to have SPT values within 15 to that. And it goes on and on for less stiffer materials. So for the same seismic line MASW 300, this was a site class that we determined for the site. We're having an average shear wave velocity of about 625, which falls in this category, site class B. And you can see from here, That is the site. This particular site is what we modeled to come out with a one profile for this whole length of line. MASW again, I think I've spoken about this already, about the compaction. It wasn't part of our exercise, but that is something I noticed when I was analyzing the data. President, I noticed, okay, let's see what happens. And truly, while you see some areas appear to be well compacted, but this confirmed. And this is also from Park Size, his website. He did some work recently for the Minnesota Department of Transport, where they have now produced MASW to evaluate compaction on road. And this is what they are doing. And we can also try and also mimic that today. Bedrock velocity. If you see this dispersion image, this is also another site in Jowli. With this one work in Jowli. You could see again a constant velocity between 40. These are the shallow layer. The 40 heads all the way coming down here, and the lower frequencies are our qualities. Low frequency, the same basic equation. V is equal to F lambda. That is what we use in coming out with all these velocities. So once you have longer wavelengths, you have low frequencies, and then deeper layers. And now high frequency, shorter wavelengths, and then shallow layers. So we could see the deflection point here. Around, let's say, about 3 meters. If you do the calculations, about 3.something meters around, it changes, the ground changes to become much more steeper, get into the bedrock velocities. So MASW again, you can use to do what? To identify or locate the bedrock velocities or determine the bedrock velocities. And this is what I was talking about for the subgrade reaction calculations. I picked this from Gazeta's 1983. And you can see the parameters he uses for the determination of the static stiffness for circular and straight foundations. He uses the G here, the Poisson ratio, and then the elastic moduli, E. I think he had an example where it's a circular foundation with radius, all that, and then the elastic moduli, this, and then the Poisson ratio. So you calculate some of the horizontal and vertical rotation and static stiffness. So the G, the E, and the Poisson ratio is very, very important in calculating subgrade reaction. And we can measure basically. And some advantages of MASW. MASW is one of the easiest seismic methods that provides reliable results. In comparison to the conventional drilling fully implemented on the ground surface, it's non-invasive and covers the subsurface in a continuous manner and provides a complete coverage. It is also cost-effective, efficient, and quick way to assess the subsurface and also complement available geotechnical data. You cannot just do MASW and ignore other geotechnical models. No. Section 5 of ES 5930 requires that you consider geophysics in any ground investigations, any geophysical method to complement any geotechnical borings that for your site investigations. MASW also overcomes the limitation of traditional geotechnical techniques that can only give limited and localized information for the lack of lateral characterization. Assuming the 2D section that I showed, if we have to drill series of boreholes, if we have to characterize the site in that long profile, that means we have to drill series of boreholes before we can connect them together and make meaningful interpretation for the subsurface. But with the MASW, it's easy. If it's 1 kilometer, you can run it. So assuming you have to get a whole profile for a 1 kilometer with only 10 borers or boreholes, that's also very expensive. The equipment and accessories are lightweight and can easily be deployed to hard-to-reach areas. Typical example is this particular site, the old Aluwes site, where Pioneer Food can have put up a new processing plant or factory. One of the areas that we conducted the survey was a whole complete warehouse covered, and no way could we take in a geotechnical to get the information that was required at this particular area. So what we had to do was again conduct MASW. In this case, we use both. You can see 2 different types of geophones. I don't know if you can see it clearly, but there are 2 different types. One is the vertical geophone, and the other is the horizontal geophone. The vertical geophone is of 4.5 natural frequency. That is what we use for the MASW. There are times some reports have come up, seen them. They don't even specify the geophone type that was. But I assume is the 10 hertz. Fine. 10 hertz for shallow refraction and all that can extract something specific, but it wouldn't go deep enough to probe up to the top 30 meters that we are looking for. So the vertical geophones we use to only acquire the vertical component of Rayleigh waves. And then the horizontal geophones, we use that to also acquire the radial component of Rayleigh waves, and then the log waves as well. You know, the log waves are the ground rule. In any ground motion, they come in that direction. The horizontal, see them like that. So once we're able to acquire all these 3 components, the vertical component, the radial component, all of Rayleigh waves, the log waves, we can jointly analyze to come out with a more construed VS profile. So in comparison for the seismic survey and MASW, seismic survey and the conventional drilling, you could see this site. They drill some 2 boreholes and try to connect or infer that, oh, that's how ground surface behaves. But with the geophysics, we're able to show that the ground is not as it is here, but it's rather undulating. And this is a typical example from the previous slide I showed earlier for the ridge site. This is not an MASW section. This is a typical 2D refraction tomogram. I brought it here because it's a site investigated where they've already done some boreholes around human ridge thereabout. And this is where the first borehole number 6, terminated. The second borehole, number 4, also terminated around depth. And that was, after conducting this survey, the geophysics, this time refraction, you could see how the ground profile behaved. And over here, we're going to put about 18 stories. So using geophysics, we're able to come out and understand the ground better compared with just having some few boreholes around and collect. You can easily miss some that is of great interest. Now I come to passive seismic. Passive seismic is a horizontal vertical aspect ratio. It's a passive seismic method introduced by Nakamaru in 1989. It measures the ambient noise produced by wind or ocean waves. HVSR explores the ambient seismic noise signal, estimates properties of unconsolidated overburden sediment, with the HVSR, we are interested in the impedance contrast. When I say impedance contrast, we're talking about the soft layer and then the stiff layer. So that we obtain from HVSR differentiates these two, the soft and then the stiff or stiffer material. So by measuring the three components of size peak points over time, usually I use 10, 20 minutes. HVSR can determine the fundamental resonance frequency of the overbedding material. The sedimentary layer overlaying the bed. By using H over HVSR, we should be able to measure the peak frequencies. And then out of peak frequencies, we're able to get the H over B, which is the ratio or amplification factor. How the ground will amplify at what factor? Should there be any ground? So HVSR is used in the analysis, site response analysis using HVSR or H over V spectral ratio on ambient vibration is a fundamental part, quite evaluates local site effect and assessing seismic hazard earthquake prone. What it means is that if we're able to measure or determine the site peak frequency, we're able to know what soil is coming in terms of H resonance frequency. This will provide a structural engineer as to what frequency is supposed to also design the structure to avoid resonance. Because the moment the soil, the frequency for the soil and that for the structure resonate, we all know what will happen. Collapse. I think recently a church building collapsed around Portiano area. I think it was oscillating or vibrating at its own frequency. The instrument that they use as what vibrating frequencies, nobody knows. What desired frequency was used for the structure, nobody knows. Because nothing happened. There wasn't any tremor or nothing. Out of those, everything collapsed. So out of the peak frequency that we detect or measure using the passive seismic, we can also estimate the shear wave velocity. For instance, if you have a borehole drill and I have HVSR measure, after that we can use the resonance frequency formula, which is F dot equal to Vs over the 4H, where your H is the thickness of the overbearing material. So if you have that information and I put H over V at your site and I have the frequency, I should be able to at least give you an estimation of the shear wave velocity for that. And by absorption is that medium will have a constant velocity, just as I showed you in the previous discussion image. So F naught, out of that, okay, we get the HVSR out of it, again, we can get the amplification factor. Then the amplification factor, through that, again, we can also calculate the vulnerability index for a site based on Nakamaru again. He has a relationship which equates to the vulnerability index, which equates to the square root of the amplification factor over the frequency. The frequency is your peak frequency, and that should give you your vulnerability index. And it gives you a range that around 1995, there was some earthquake, and he determined that areas that had vulnerability index of more than 20 experienced some damage of certain earthquake magnitude. So this is a typical HVSR acquisition at a site at Oman Ridge. And again, the north, south, east, west, all the components of the ambient lines was measured. And then we analyzed the data using one of our industry software, Polysurface. and then also the Sesame, under the Sesame criteria, and came out with the frequency for the site. And this is a typical one piece. Over here, we had a site peak frequency about 1.55 hertz and amplification factor about 4.48. So we should be able to get the vulnerability index for this site. Application of H/V. So we use to determine the impedance contrast, which I think I've talked about already. And also the vulnerability index can be calculated. We get the peak frequency, the site application factor can all be determined using the H/V method or the passive seismic. HVSR also can be used to determine the dynamic characteristics of structure through each modal frequencies. What that means is that we can use the same principle, HVSR, to determine which frequencies this building, for example, was designed by picking the data along the axis of the building. I think at one office, and you see the movement that is ongoing within the building. It's very interesting. Unfortunately, I don't have a video to show. So HVSR can also be used for vibration analysis. The same data that we acquire can also analyze it for vibration analysis. And this I've also done just to monitor the level of vibration I receive, especially while it's closer to the road, main road, Kaspa, Ouija Road. So one day I just put it down on my dining table to measure. And then also I switch off the fridge and other equipment and then put it on the ground to measure. If you see the vibration level, it's not good for humans. Yes. It also explains why sometimes I can't even sleep at night because you have a lot of traffic going. So H/V again provide an estimate of the layer thickness of sediment or shear wave velocity. Again, using the same resonance equation. Once we have any of the parameters, we should be able to determine the thickness. If, for instance, we have the frequency, we have the shear wave, we should be able to determine the thickness of the sedimentary layer overlaying the bedrock. Again, if we have any geotechnical boring information, we should also be able to determine other parameters. For example, the VS, as I said earlier, once we have the F0. In conclusion, the use of MASW and HVSR methodic geotechnical site investigations are a means of acquiring subsurface information to supplement available geotechnical boring data. So it cannot be done alone. You need to have geotechnical information available for you to correlate what physical method are you use. You cannot only use physics and then think all it right now. We don't recommend that. Data acquisition is non-invasive and also quick to gather. In Dabakala, for instance, it was a 2-kilometer line. Within 4 days, it was done. And I remember the experience we also had conduct a similar survey at Nimwanda half enough. 9 days, then we still have the streamer. It took us to get it done. The streamer makes the work easier and simpler and faster. Again, less labor is required. Usually 1 to 2 persons should be enough to acquire H/V or MASW data. Just get someone, the hammering, and then another to be taking care of recording the data. It is cheap compared with having to drill a series of boreholes to provide information in a continuous profile. The MASW, if you have a very big site, you want to drill how many boreholes you can complement geophysics. That's BS 5930 section 5 wise. That consider geophysics in every ground investigations. Its in-situ measurement of shear wave velocity. In-situ measurement of shear wave velocity can be used to estimate the low settlement behavior of shallow end foundations. That again goes back to the Gatesas, where he was using the elastic modular Young's multiply and the Poisson for foundation stiffness calculation or sub-grade reaction calculation. The VS is also used to estimate the small strain Jones modulus and shear moduli underlying structure. The Poisson ratio, sorry, there's a spelling error here. Poisson ratio and then the end value. You can all estimate the end values, even the alternate bearing capacity. You can estimate all that using a more constructive VS. Like I said earlier, your picking of fundamental mode is wrong. Everything about your VS will be wrong. So you need to understand it. Everything about your VS will be wrong. That's the end. Engineer Kofi Boateng Emmanuel. Thank you very much. Let's give him a round of applause. And those online, we are very grateful for your time for staying with us. Now, Zoom wants to discuss. I'm sure you have listened to Engineer Mike top card discussion on DCP and the geophysics. So let's give preference to those online. Do we have somebody online? Agnes, you want to talk? Do you have somebody online? Sorry? No hands online. Okay, we'll come here. Anybody here? Okay, Engineer Pinker. One cast first and got trouble.
I'm John F. Pinker. Technically, I think Engineer Abnadu has done a good presentation. I admire that. But what is left is the use of this erroneous use of this DCPT or whatever it is. You will see that most of these reports, which comes out of this, are all products from the institution. You open the last page and you see and a professional stamp there. You read it and you will see that the person who wrote it even doesn't understand the technical. And it has become that the geotechnical engineer has become one of the cheapest, whether it's a practice or profession or what it is. Anybody can get up and say, now technicians are using soil reports. They will get a professional engineer to stamp. They will not read. You read it and you see them mixing up allowable bearing capacity, safe bearing capacity, and net bearing capacity, all bearing capacity, they jump up. So what do we have to do? How do we separate the boys from the men? The professional geotechnical engineer and those quack geotechnical engineers. This is the main axiom. So I will teach the institution to find a way, or Mr. Kunedu should try to put up a position paper, since he is the chairman of that part, about the use, the erroneous use of this DCP. When I see something like that, anyway.
Thank you very much. Any other? Okay, I'll ask a question. Can you go to the Kunedu slide? The one with the formula. Saglaran, right? No, the first one. The dark one. I think one of the slides. For me, we should even not encourage this because it doesn't make any sense in physics. It doesn't make any sense in physics tomorrow. So I want to put that up. Let's go back. No, the other one. Yes, this one. RD is equal to M square H. So what's the variable here? It's E, right? Because all the rest are constant for a particular length of rod.
Yeah, for particular.
So E is the variable here. So we have y equals 1 over x, or y equals k over x, where the k is constant. You see. So what does it tell you? For me, it means that if you lifted the hammer, which is the reference, which is 0, it means that H is what? 0. If you brought the hammer up, the DCB, that level is 0. Okay? So it means that H is 0. So if H is 0, what is R? 0. So it means that if you put the DCB on the ground, it should move like it's going through water to move. But that's not the case. So in terms of physics, this equation can, I don't believe in that. It doesn't make sense. So nobody should use DCB for his or her work. This one defines the laws of physics. Okay? So you don't need to use that. Do you understand? Yes. What I'm saying, look at the relationship. It's equal, it's behaving like y is equal to k over x, which is, you see that, because the variable here is a small, that's what we are measuring. The rest are constant for a particular segment of rod, that's the 1 meter rod. You see, so assuming I have lifted the rod to, the hammer, where I want to start releasing it. That's to get that's to find the H. So H goes to 0 to the 57 point something, the 5 something that the friend mentioned. So if H is 0, what's the R, the point resistance? It's just 0. No, that's not correct. But that's not correct. In real life, if the hammer up, the DCB is still standing. So if that's 0, that means that the thing should go through like through water. So it defines this. Something must oppose or resist the DCB from going through 0. And that's a constant. Why? Because the MX plus C. So the way they derive in is wrong. I think I wrote a paper on it. I'll share it later on with you. There's a guy right now who has done serious critique about this. You should look at it. Okay. So for me, we should not encourage using this approach. It will not. It's erroneous. It's even you are too mild on that. It doesn't define proper physics content. Or you don't see, you look at the model. Or you don't. No, look at the model. I'm starting the model. I work with models a lot. If it's H0, it means that R is 0. So at the point of start of the DCB, it means that your point, what point is that your point is at 0. But it's not correct. Otherwise, your DCB should go to as going to water 0. But that's not what we see in reality. Those who use DCB. So the technical agree. Okay, that's my beef on that. So, Engineer Peter.
With this, the 30R and this, I think it's originated for us with the Dutch formula. Now, most of the users, you will see that they normally quote. I've seen about 5 reports. They start the deduction. They will first quote SKM Pedu and the time. Because that formula was quoted in one of the ISSME. I've got the paper. And they will start quoting the time. So sometimes I question what has come of the condition which is attached the use of it. You see, that's why initially I said those who have been using this are not really technical engineers who understand what actually entails, because they normally put SK and SK and instead of
Thank you very much. You see, let me also encourage you. We are engineers. We shouldn't develop the habit of always going to the internet and what's the someone else what's the correlation between DCP and ST or S? No. See, geotech environment is one of the areas that you have a lot of correlation and lot of conflict. Because you are doing a lot. You can get somebody in Pakistan doing the same thing, getting different results. Somebody from Kenya is getting different, and you want the one from Togo, you want the one from Pakistan. So you have to understand, read the work of that individual and under which conditions or criteria a person develops such model. It's very, very important. We have on the line. David.
Yes, good evening, fellow engineers. I'm happy for this presentation this evening. I'm very grateful. It's been eye-opening. In fact, you've touched a very sensitive topic, and I think this presentation should not be the end on this matter of use of DCPT, but we should also create another platform. Now, the system has been opened up, so we can go and interrogate and come back. I want to, the topic, that particular paper, senior engineer Pinkra was referring to by Ampedu, I would want, I think I've shared it on the chat area. So I want it to be available for everyone to go and read it. And then under forum, when we meet, we can interrogate it. I think the relations of 30R is too overestimated. That paper referred to Ampedu and Giche is actually based on a model footing which was conducted at Tech KNUST 2008. And that paper published 2000 and a conference paper published in 2009. A model footing was done and the model footing was loaded. So it failed. And then at another side of that same material, the DCPT was performed. So the point is at a particular point where you have DCPT D value and then the failure of the model. And then the two were correlated. I think with this small background, we should be able to go and look for that paper, go around it, and then another forum, we can interrogate it. Thank you very much. Thank you, Engineer Ode. Thank you, Engineer Konedu. I'm grateful.
Thank you, David Ode. Now, another point of discussion is, I think the primary source of bearing capacity, we all know, is from Tezaki, right? Let's look at the theory side of it, is the Tezaki. What are the parameters in there? You're interested in the depth, you're interested in the footing size, you're interested in the soil parameters as the density, you're interested in the maybe what do you call the sea. Okay, share. So what is the difference between that and why we're using this to estimate bearing capacity? I don't get it. So for me, anything about bearing capacity without B, you're not talking about bearing capacity. Seriously, anything discussed about bearing capacity without the reference to depth or the reference to any other, then you are not really discussing bearing capacity. You understand? If you want to go by the theory, let's look at the theory, and then if you want to produce a kind of an empirical sort of relation, how do we marry the two? We should look at it carefully again. And seriously now, if Eurocode is not interested in the Tazaki and PEX charts, you can refer to the EC7. They are not interested in the Tazaki and PEX charts. Okay? They want you to use calculation. You need to do geotech design. Probably coming up, I mean, you guys are some of our senior. If you meet these white guys, this local, when they give you job, it's no sweat. But if you meet the foreigners who understand the stuff and they give you you ask your finger, you will not sleep. No, I'm seriously telling you, you really have to know your stuff to engage these guys. Otherwise, you disgrace yourself. So you cannot just do that structure. Some of the structure engineers will tell you, I want bearing capacity at every depth. What is it for? You understand? So please, there are a lot of geotechnical models, equations, but using the approval, you need to understand what you are doing. Otherwise, when your report comes to some of us, will ask a lot of questions. Uncle, you have to talk. Uncle, you have to talk. What you are listening? Okay. Any question online? Do you have anybody there? Yeah. Yeah, Mike.
Well, for those who use the dynamic probing approach seriously, what they normally do is the value they get, they tend to correlate it to SPTM value, and then they produce a bearing capacity equation to finish it. So there are certain software, when you do this, software will ask, what is you have to make certain assumptions. What footing size are you anticipating? What depth of footing are you talking about? And what is the design load that you're going to put on the ground? It is only after it has this, then it will give you a bearing capacity for a certain assumed settlement, so to speak. So it's not normally nobody goes straight to things like this. This is the shortcut menu. But even if you want to do shortcut, do it safely. That's the whole point. Because like I showed in that diagram, that one sketch, everything I've spoken about is encapsulated in that the graph. Now, forward, go, here. Everything is encapsulated in this. You see, the red line is what is happening.
Actually, the foundation was founded as, let's say, 1 meter.
Yeah.
Okay.
Yeah.
Is that correct to choose that parameter as the foundation?
Which?
Yes, and then apart from that, you mentioned of the zone of
Influence, yeah.
So that you have to consider that whole zone as a factor.
Yeah.
You understand? Either you want to evaluate based on the weighted average needs to get a typical value for that, or you set the explanation for that. You understand my point? Because you are getting 1.88, let's say, you are getting a maximum value, which is about 8
at 1 meter. The blue.
That's 3.348.
Yeah, 348, 110, yeah.
So you see, and
you are choosing that particular depth as your foundation depth.
Yeah.
You cannot recommend 348 as a allowable or whatever bearing capacity you are talking about. You understand? Because you should think about what the zone of influence.
Yeah.
That's why Geotechnical said that if you chose 1 meter, what about if you look at 1.2?
Yeah.
Because there is stress distribution below the footing.
Yep.
Okay, that is why if any structure here asks you give me settlement, tell it give me the load. If you ask give me the load, tell it you can't give settlement. Okay, you cannot calculate settlement without knowing the imposed load. Anytime somebody asks you to give you settlement, give you the imposed load. If you are not giving them, then you can't give the settlement. All right, we all want to work together. You should let them know the way your practice works. We cannot go and tell somebody how you should practice his profession. In our profession, if you want me to give you value set, you should give me the load. Nothing like Gadochi, that's all. If you can't give me, I also can't give you the value. That's all.
Yeah, and also this business of doing just 1 or 2 points on the site, you see, is very, very dangerous. It's very, very, very dangerous.
You'd be like, was it pure APS or something?
Yeah. You must like I said, the results must be representative of the site. So you must have quite a lot of data. And you see, one thing which worries me is that the DCP, if you should use it, actually the usage is quite simple. So at least do plenty and then do some statistical analysis of the spread. And you can, but like this, you do this, maybe the next one has this, which one do you choose? It's a bit difficult. So, and like when your finger said, if I tell people that by my virtue of my training and practice, I am a geotechnical engineer and water guy, they have a problem. They do. But when people can come and say, oh, I am a structural and geotech, they don't have a problem. They can say, I am a water and geotech. No, water and geotech. Anything that precedes, the geotech is just a tag on. But if you identify yourself as primarily a geotech, and you tell them you can do other things, hey, but all the other people can do geotech. That's how, and this stamp that we give with this civil engineer thing on it. Some people write this and will tell you that, oh, the thing is very, very dense clay. You see it all the time. And sometimes what they even say, oh, F. Hard F. I mean, when you see that, you know that this man doesn't have the geological background. You see, but he has a civil engineer stamp. And because of that, he can stamp a geotechnical report. So that's what you're saying, that we have to find a way of this thing. And that is why I'm trying to propose that somehow we must come out with some guidelines for timely review of these things before people get away with it. You see, me, what I'm doing now is, for me now, is advocacy. I think people should tell them about what to do the advocacy first. And when we've done enough of it, then we'll start doing the monitoring and enforcement. It's quite easy. Because any place that you have set this machine and done this, I can bring a ESH machine just to punch hole in this thing to tell you that it is not 340 at one thing. It is not. When you apply, and like I said in the beginning, the choice of the equipment must be influenced by the geotechnical site conditions and the equipment limitations. Yeah. They are doing it all over the place. Because yes, they can just stamp and walk away. And you see this building collapsing that we are looking at, the DCP has surfaced in some of the places. It has. It has.
Almost all the collapse buildings that occurred about 2
and if
3
you
months
read the reports and stuff. Yeah. But it's like Mr. Finger said, they all have DHI stamps of them.
Yeah. Okay, so if okay, I let engineer, if I have to give you advice, you bury me.
I think that there's a fundamental problem when you know, for a structure to be built, one of the first point of engagement is that with the geotechnical engineer. And then the geotechnical engineer asks the structural engineer, what is the load? I think in doing so, the geotechnical engineer must give a range, because at that moment, the structural engineer doesn't know the load that is, the stress. So he should give a range
of the very resistance.
Yes. So what I say, the range of pressure, you know, bearing pressure, that's the structural engineer, you know, and you envisage to come up.
Now, you see, that's where I have issues with my friend's structural engineers. The point is that, to be honest with you, where do they start their designs from? They start from the top. They don't start their designs from the foundation. They start their designs from the top. And before they get to the foundation, you understand? So they don't even need to wait for me to start their design. They only had me when I go to site, all that I want architectural block plan to be able to distribute my boreholes. Okay, I've got my data, I'm writing my report. You've been keeping the architectural design, you are doing your structural work, right? You are starting from the top. When we all get to the bottom, then now we come to the top. I don't need to do rings. Because you see, let's granted that we are using the Kazaki and PEG chart. If you want to estimate the allowable bearing capacity with the Kazaki and PEG chart, you need the N value and then the B in the American, right? You need the N value and the B. Now, assuming range, I chose B. Assuming I chose B, corresponding to an N value, and I got an allowable parameter, and I gave. Now, you are going to put that value, assuming bearing capacity of 200, into your software. Now, once you plug that into your software and your load, your software will be a various putting sizes. You understand? Now, the value of me is maybe 1.2 weight of, and your software is another thing that because of your load is giving you 2 meters. And you have to use my allowable capacity. Once the P has varied, it means that the allowable bearing capacity is not correct. You understand? That's why the Eurocode says that geotech and structural engineers must work together. When we get to the foundation level, I can start to tell the so you 200. Come out with your size, then fit to me. My duty to validate. So I'll pick your load, I'll pick the footing size, I'll get my soil parameters I've developed, then I'll deduce the over design factor. You understand? Then I'll know whether load and activity is safe or not in terms of the factor of safety. So structure engineers, they don't need to wait for us. They have to start their design from the top, the roof. They don't need to wait for it to take reports to do their design. They don't. The difficulty is that because most of them are using software to design their work, when they get to the foundation, the software asks for allowed bearing capacity. That's where we have the problem. And it's a problem we need to solve. That bearing capacity is not just a fixed value. It is based on parameters, footing sizes, then soil strength parameters and stuff like that. So it's not something you can just afford. The geotech must also support the system or the design to take a decision on where to put the foundation. It's not the work of the structural engineer to tell you where he wants to put the foundation. You should let them know. I tell them all the time. That it is not your work to tell me where the foundation. It's my decision as a geotech engineer to tell you where you need to put the foundation. Okay? If you think that you have a problem, let's come back to me and let me take a decision. Because something happened and we are doing forest investigation, you the geotech person, you'll be in trouble. Yes, you'll be in trouble. So we should work as a group. They should know their limit. We also know their limit, our limit. Okay? It's very, very important. Structural engineers, they have their limit. Geotech engineers, they have their limit. We all work together. And then we can implement an effective foundation. When you go to the top and are doing the superstructure, will come in there. Probably some of us will be checking their concrete strength for them. Do you have something online? What's the name? Hi, Jojo.
Yeah, Joe.
Go
on. Thank you very much, Engineer Kunedu. That was a very brilliant presentation. Thanks for throwing more light on the DCP issue. In fact, Prof. Ampedu made a presentation at a conference, rock science conference, on the use and abuse of the DCP for site investigation. And he pointed out some of these things that you have talked about. And in fact, one other thing he also brought out was the friction from the rod. As you go down, there's an added factor of the friction due to the contact between the rod and the walls as you go down. And that adds to the overestimation of this bearing capacity. In fact, the problem really is the correlation between the DCP-N with a bearing capacity. That is a no-go zone. It should be discouraged totally. However, I don't think we should throw away the DCP so much. We shouldn't vilify it that much, in that the information you get from the DCP can also still be used as an indication of the, the subsurface profile in terms of just the number of blows with depth. That gives some useful information. The raw data in terms of the number of blows with depth, that can give a good indication of the subsurface profile to some extent. And for foundation design, what Prof suggested, and from some research that was done, is to correlate this DCP, let's call it N value, with the SPT N value, and then go ahead to use that for the bearing capacity computation using the Terzaghi or the Meyerhof approach. And with that, we have been able to even publish some paper on that. And I think that should be the direction we should go. Correlating that, creating that critical link between the DCP-N and then the SPT-N value, so that information from the DCP can be reasonably used for some foundation design. The challenges, with site investigation when you are working in enclosed spaces, like in a warehouse, already built up area, you'll be able to take in a whole rig to do your drilling. But you would still need to get some information from there. And I think the DCP can still get you some sort of decent information. However, it shouldn't be correlated straight away to bearing capacity, but rather we should try and convert this N to the SPT-N, and that can then be used for foundation design. I think if we are able to get this paper he wrote on the use and abuse of the DCP, it would enlighten members a lot on the applications of DCP. Because, in fact, this meeting, a friend of mine, a structural engineer, saw the poster and sent it to me and was alarmed that, hey, this is what your people are saying. So does that mean the information we've been having from, DCP is bad? Well, it's good that this is coming up. Then we'll start to sensitize them on the proper way of doing site investigation and getting qualified people to do these investigations. I have a question for the second presenter. I don't know if I can go ahead to ask.
Please go ahead.
Thank you. He mentioned about the MASW being able to give the PGA, site-specific PGA. And I wanted to find out whether he has looked at the values he has obtained so far from works done in Ghana with the PGA recommended from this seismic risk map by Amonuneza. How did his values that he has obtained so far from works, correlate with what has been published by Amonuneza in terms of putting Ghana in a certain risk map zone? I just want him to throw a bit light on that. Thank you.
Thank you very much, Jojo. So Kofi will answer that, then PP Amonuneza will also ask the question, all right? Kofi.
Yeah, thank you, Jojo, for your question. From the work so far done, what I've noticed is that the PGA that is being used is overestimated. Like I made mention earlier, some sites, after conducting the survey and coming out with a specific VS for the site. For example, I made mention of a site where they plan or they design to site class C. that was around Abraka. But when we conducted the survey, it was a typical site class B. So the VS that we obtained, we use that to calculate the site-specific PTA using the deep soil application. And that was far less compared with the PTA that was recommended to be used for the design. And this saves cost. They were estimating around 0.3 based on that HVSR and so. But when we did it, we were getting around 0.1, something 1.2. So we recommended 0.2. And that is huge in terms of cost construction. Typical example is also another site where that was around the AU phase area. We conducted a survey. They planned to go with a site class of, I think that was also C, but then they recommended a PTA of 0.2. We got a site class to C, that the PTA that we got was 0.35 after the modeling. And again, there are so many of them that will come up. So the key point here is that if you get your VS correct, you get a very well construed VS, then you shouldn't go wrong in getting your PTA or site-specific PTA for the site. If you are not careful, as I explained earlier, the dispersion curve or the dispersion image, many a times people get it wrong in picking of the fundamental mode. Probably another time I will come with another presentation on the way to also acquire a more reliable using the wholly surface approach, where several components are acquired and jointly analyzed to give you a more defined piece. So we are considering all components, the radial, vertical, log width, the RPM, radial, rally particle motion, H over V. We jointly analyze any of them to give you the more the better, to give you a more reliable PS. But if your PS is wrong, definitely the rest of the deductions that you take out of the PS will be wrong. I don't know if my answer is well explained to you. Thank you.
Thank you very much. So, PB.
I've seen a lot of what do you call it, models and whatnot, displayed over here. But the basic question as engineers, but is our institution is tracking very bad publicity on account of the buildings that have collapsed. And this is the root of the building collapse. What is the top doing about it? Because it's driving the name of it down the drain.
Thank you very much. Chairman, you have a responsibility around. If you want to add post. Okay.
I think I have two copies on what is done. First is another excellent presentation. One thing, I'm not a designer, but I've been interacting with a lot of structural design. The PGA, which has been published, or if you go to Amonisa, they said it's a protected. So sometimes it's risky to use it. If you want to have a correct one, I would recommend that some work is done on the field because it's a protector. Most of the structure, I don't think in Accra yet, they've been using the 0.35, something like that. Most of them, you see, the local designers have been using between 0.2 and 0.25. That is by my experience that I have encountered. Number two, when you look at the geophysical, he said advantages were that some equipment are versatile. It is less expensive and all that. It looks like cost of conducting a geophysical study. Sometimes they look very good, and it's to give some supplement to the boring geotechnical. So if you are going to do technical investigation and you go in, please support me with some values, let me get some, something you think professional. And the man comes with a cost, because he said somewhere there are 2 or 3 people on the field, and all the equipment I saw is from ice chest box, and a seat. He's always sitting down. And he comes with a cost which is almost about half of Geotechnical. See, some of these things put crimes of the year. You see, so can he educate me what actually the input? Is it the interpretation or what is it? Because as already said, cost effective data. So this is what it is. Because here I'm a professional man. I always
you don't use software, so you don't charge for software use. Now, yes, software.
Thank you, Senior Engineer Bankra. Chief. I always give you a very big discount of this company. Let me what goes in the pack size software alone costs $5,500 US for the one I use to produce the 2D section for the MASW. That one alone costs $5,500 US, excluding shipping and whatever handling or whatever. The Holy Surface software that I use for the H/V analysis, that one does both the vibration, H/V, and what using also the same 3C geophone to acquire active data. That one alone costs 4,500 euros. A lot of investment has to be for us to get accurate information about the ground. So definitely, no, the hardware itself is another. That geophone, that one you see, is about $3,000. That 3C geophone to be able to give you the fundamental frequency for the site, the H/V. It's 3,000 US. Because I give you a lot of discount. but for a typical site, let's say one plot, if 2 seismic lines, for each seismic line I do 2 H/V. So let's say for 4 H/V, 2 seismic lines, it's less than $3,000, which I think is it's very fair. The kind of detailing you get, it's fair. Less than how much? It's fair. Including software use, data processing, my professional fee, everything goes in there. No, not there's a lot has gone in. Honestly speaking, but I can't overcharge. They are all put up. Yes, I understand. It's all put up. I'm not overcharging, but I give him a lot of discount.
Mike,
honestly.
With respect to this question, we have a PhD student. We have somebody doing PhD. We want to look at with the current data that we have collected. We have a PhD student working on producing some of this map within the zones of Accra. So, in when she finishes, once we have found more data, we can still put into the model to generate the maps. Okay. What we're going to do is that, Engineer what talked about getting the VS. The VS is a very important parameter. Now, in developing the PA, you need what we call the big data. Here, geological is a bit handicapped when it comes to big data. And big data is well published somewhere, like the Chichi earthquake has back to about 7.7. You can get other earthquakes with different magnitudes. Then you can get your quick data. Once you get the quick data and the VS with your soil profile with the site, you can run the software to get the site PGA. So what then also means that we want to vary the quick data. For example, based on their month. So maybe because Ghana here we are having what we have 4, we have highest 6.5 thereabout. So now the T is 7.7. We want to try an S-peak around 6 and see what we get in terms of the PGA. If there's a like and see if there's some variation in there. Okay, then now it depends on you the engineer in terms of your choice. You want to go extreme, or you want to be in the middle, or you want to do. So we are working on that. I'm sure by next year she'll be done with this and then move forward. Yeah, man.
Okay, so Jojo, I like to address your concern. But what we meant would be true. We want to prohibit the use of it. You see, it is reached dangerous proportion. It's like a knife. Knives can be used for a lot of good things, but we don't allow children to play with knives. If academics want to continue researching so that later on they can give us good correlations that deal with friction, that with all the other issues, because like I said, we want to have a test equipment that can at least 4 meters, give us reliable results. If you can convince us the energy of 8 kilograms of weight is enough, basically 4 meters well, you show us how to take out friction and all that, and it's accurate, fine. Then we'll look at, but for now, we don't have that. And we observed for the past years. Right now, it is become scandalous what is happening. The other thing is that, please go to the conclusions. I put something in red. I wanted to pay attention to it. We've been struggling to get investments into the system by way of standard brakes and other equipment. What is happening now is because of this rampant use of the DCP, even the few that have come to the country over the last 10 years are basically just part. Because if some young, dynamic young man tells you that, I have a stamp GHI, I can write a report for you for 3,000. Why would you want to go and put some old man like Sabinka and pay 15,000? Immediately, they don't compare anything. Like, he just checked, there's a guy have a stamp. Yes. He says you write for 3,000. Last week, somebody called me. I have a job for you. Yes, I hear you mistakes. They have told me that it's 4,000. I said, what? Say yes. The contractor has given him the list of all the payments must speak. And soil test is one of them. It's 4,000. So after having the information, he looked around who do soil test, and he knows that I do it, and I've been doing it for a long time. So he's bringing me a job, 4,000. Wants to build a 6-story structure somewhere. 4,000. I mean, who would invest in a rig that accurate? Look at what is about now is suffering. He's going to be all these standard equipment. He's only like that we don't have alternatives for this, like be a proof man. Yeah. You know, so some of these things we have to regulate them. We are not saying that we should. No, you academics continue till eventually you can come out something that works well, fine, we then accept. But for now, what we are doing here is the beginning of another specific campaign. We are going to develop a position paper on this, and then we intend to approach the hearing council and the Ghana Standards Authority, all those people, so that what we can't control now, we take it out. And then, like we said, even the big things which are there, we would like to have them properly calibrated so that we can use them properly. It doesn't matter whether it's time for AESL or Geo, what is it?
More people.
So yes, we intend to try and sanitize the system again so that PB, as you said, what are we doing? These are the things that we want to do. We've identified very obvious ones. Want to do them, then gradually, we'll try to regulate the industry a bit better.
Before there is a collaboration between engineering council and yes, that's standard authority. And we can pushing this thing from that angle. The key is that we need your support in terms of effort. When the chairman calls for members come and let's support development of balance, let's come. Because once we have to use the unit to enhance the paper, and from there we can make like a technical standard document which will push for the system. And you see, one aspect that is a client request, I've got someone to do it cheaper for me. Getting it, yeah. Oh, yeah. It's very insulting. And you see, the guy has not given you any scope. He doesn't understand the way. But he thinks that you have the content, contains ball and all, and someone has the content, you contain TCP and test, so it's cheaper. And he's going to do the same. So you say, thank you very much. I've got somebody. You say, okay, fine, go. And some of them, of course, we have opportunities on the assembly application principle. What you get there, they want to throw the report away. Oh, yes, that's because we throw it away. Then they'll put it proper. Let me support you with what they said. In fact, about a month ago, I even called that community. There was this Indian, a friend of mine, Sophia, asked the code for 10-story building. After giving detailed quotation on the tech, there was a counter from somebody. He showed me what I was charging was about 110 for the house. I said, what are you going to do? So this is what the man said he could do. Less than. I said, hey, let me go through the test requirements that you want. And I found something CBR. I said, you know what? Back he's using the dynamic code penetrometer for TRL. So yeah. I wish you could have shown us the TRL dynamic cone penetrometer that we use for road. I haven't seen it. Yeah. We use that DCP for designing road pavement design. And when I saw that list with the test requirement for CBS, no, this man is using the TRL DCP. And that has also gotten into the system and people are using. So I wish you have shown us the picture of that TRL DCP and the DCP for site identification. Yeah, but that one, the depth probe is just within maybe 1 meter. It's okay. It's just for the road assessment. So what I want to say is that we can disqualify that for that's what somebody shows. So when I saw CBR, you see the CBR, the TRL is for road movement design. And he is trying to do that and then maybe do some correction for very capacity.
Okay, so the other point is that the other point I want to point out is a lot of this being done by young men. They think they are surviving. But you see, if you don't allow us to grow, we can't employ. Now you have companies with equipment and things. They more or less laid all the guys off because they can't sustain the business using the correct kind of equipment and things. And this same young men will then say that those people are not doing anything for us. But before you are taking your own. Anyway, Chairman, so thank you. I think
as our senior man said, the institution, I don't know what you people have to have the position paper on that. Now, I came across a consultant who is 3 years old after graduation. He has done of the institution, a stamp, a professional stamp, because he just had 3 years. Nobody mentored you. I think he during his national service, he happened to work for somebody in the technical area, so he was able to acquire little knowledge that, and after he was not getting work, after the project was over, he was sitting home and became a consultant. And he kept work. In fact, I do a report of it. I thought, I said, do you know what you are doing is very, very dangerous. Oh, Edmund, said, oh, have a son. And 3 years old after graduation, the consultant. And this is work. So I also charge the membership committee the way they vet people to give them stuff. Now, what you do is bring your career report. Then you write an exam, they interview you. Look like the way they interview this time, we need, because we need people, we need money. So I think we've been brushing over. So with you guys, please, let's different the way you issue this stamp. That's my competition. Because now anybody can have get the stamp.
Thank you very much. I think we have done very, very well. Let's clap for ourselves. When we started, we had over 100 online. How many are we online now? Okay. We have how many? We have 58 now. We also have probably about 20, a little about 20 here. So, and I'm sure that the discussions have. We have some questions online. Okay, please, who are they? What's the name? Michael. Michael, please go on. Michael, please go on.
Yeah, thank you very much for the opportunity, and good evening to all of us who are at the center. Just for those who know us to get to know us better, this is Benoni, and I have been listening with keen interest the presentations and the discussions, and one thing that is paramount or an underlying factor is that there's a lot of discussion on the merits and demerits of each investigation approach of data that can be obtained. It's important for us to understand that all our codes of practice indicate that each of the exploration approaches have deficiencies. And as such, the best way to approach a geotechnical exploration is to have a combination of this readily available techniques. I've had experience of using one of the best geophysics companies in the world in conducting some work around Northwest Africa. And we combine this with the traditional methods or the orthodox approach of explorations. And the results from this geophysics, which include the MASW, indicated that we had bedrock that could be relied on for the construction, design, and development of a harbor. But when we went in with the traditionals, we found out that what the MASW found as bedrock was actually consolidated sands. And so we ought to be cautious as professionals whenever we are going to the domain of which one is better and which one is not good. And typical comments like, when you find a VS and it's correct, then everything will be okay. I was happy when the presenter mentioned that there are various influencing factors to the accuracy of the results. And this is true. We've done a number of work all around, and sometimes these MASWs and all these vertical soundings and downholes tend to provide very deceptive results. We just have to have enough experience to identify these deficiencies and incorporate alternative exploratory methods such that when there is a problem with one data, the other data will guide you to identify them and correct them as appropriate. The second point is that the use of experienced professionals is very critical. And I was excited to hear my colleague and senior mentioning the fact that 3-year experienced guys are parading themselves as geoprofessionals and writing all kinds of reports. I have an experience where a structure to be built around Peduase was supposed to be given to my attention. The next moment, the owner says he's okay, he has a report. So I asked the engineer, has any work been done? He goes like, well, some guys came here, look at the site and went back. The next morning they have a report. No excavations, no nothing. And this was a 4-story building. Nothing, yet they have a report. And so I think one component that we need to look at more is who is preparing a report and who is signing the report. It's a very key item to mitigating some of the risks that we are facing at this moment. Also, one other thing I would like to highlight, and I'll hand over the baton to Engineer David, is the fact that most of these structures that are collapsing, we tend to have nominal reports on them and defining exactly what the problem was. But if you look into it, most of these have barely had anything to do with some level of analysis and identification of parameters for design. I'm waiting to read the findings of the investigation into the failure at is it University of Development Studies, to understand what happened there, because at least the university should have an engineer, and at least you expect that the right things were done. But these are the very things we need to look at, not just the merit of one equipment over the other and the cost effect analysis. I've actually been involved in a $1.2 million geotechnical investigations, and you find the flaws depending on the geomorphology and all of those things in various techniques of exploration. So we cannot necessarily rely on one approach and say we are okay. And I do like the conclusion from the presenter regarding the DCPs, that we cannot use the DCP as a primary tool for estimation of the shear strength parameters or bearing capacities of foundations. So this is something we need to look at. Should I just take drilling a borehole and say I got some SPT values, and because I can trust SPT values, everything is okay? Well, the Modified California has indicated that SPT can also have deficiencies. We've done a number of other tests which also show that other tests also have their deficiencies, which is enshrined in detail in all our codes of practice. Last but not least, would we prefer that people go to site, look at soils, and come and write a report without any test? Or would we prefer that a DCP equipment was sent to site and the results analyzed by an experienced person for a limited structural level of design? That's something we should look into. I believe that the basis of the publications on the DCP was to encourage people to at least undertake some basic assessments before they go ahead and design. And if we just throw it out of the door like that, then we will continue to discourage people from undertaking the things that we are encouraging them to do. This is my little submission, and thank you for your audience.
Thank you very much. What's the name again?
Benoni. Nice
Benoni,
person.
Good.
Joe.
Yes,
Thank
good.
you.
Who is the next person, please?
David teacher.
Alku, please go on.
Yeah, thank you very much for the opportunity once more. This question goes to Engineer Boaten. I just want to find out, why are you using magnitude 7.7 for your model? The earlier microzonation map you make reference to was based on 6.5. I think that's based on the 1930s earthquake. Why are you using the 7.7? Can you look at the 6.5 so we can compare apples to apples and not apples to oranges? That's number one. Number two, we have to make a decision. Just like Benoni said, Engineer Benoni said, some 2 or 3 years ago, we started developing guidelines for geotech practice within Ghana here. Can we visit that guidelines again, bring the draft out and start actively contributing to it? So that becomes the direction for us. What other one I want to add is, can we also start encouraging the geotech community, instead of the current DCPT as we have with all the cited flaws, can we be looking at the DPL, the dynamic probe lights? So these are the questions that I've put out there. Thank you very much.
Thank you, Engineer Oku. The choice of the magnitude 7.7 earthquake was just for me to go to the stream, because we haven't had that here in Ghana. We don't have the big data. It's not even available. So I decided to go the extreme using 7.7 ground motion data, which is easily available. You can equally use the 6.4 if it's available. We tried to get one from political states. If you are going to give us today or tomorrow, I don't know. But then the choice of 7.7 was to just go the stream, see what happens, what I get, compare with what I would experience so far. So the PhD student here, Roberta, is working. She's working on something similar, using various big data to analyze similar figures for specific sites and see what come out. So that will also be shared once the results are ready. Have I answered your question clearly? Engineer Oku?
David.
David, what I mentioned was that moving ahead, we try to develop the guidelines for the geotechnical investigation. What I said actually was guidelines for timely review, but I'm sure in doing that, we could do the basic guidelines for the conduct of the investigations itself, so that we can have a comprehensive package. So we are looking to doing that. This is only the beginning, raising awareness, and then we'll continue discussing. Eventually, we'll get something that we should all be comfortable with. Thanks.
All right, so I think we are done, right? All right, so gentlemen and colleagues, thank you very much. I really appreciate your time for coming. So we'll call on you again, maybe in the next couple of weeks for another seminar. We need to come, we need to share ideas, we need to update our knowledge, and then we need to move the industry forward. Thank you very much for coming. See you soon. Bye-bye. Oh, okay.